Hi and welcome to another MoTeC webinar. My name's Pete Swinney and today it's part 5 of our introduction to M1 diesel tuning. And today's subject is boost control. Lot to cover off here. We're going to go through the different types of turbos you find on a diesel engine. Making boost or getting the airflow going on a diesel engine is critical. It's kind of one of those limiting factors of power that a diesel engine has. The more fuel and the more boost, the more power, and that's about it. After that, it's mechanical strength. So having the maximum possible boost being available at all times is kind of your main aim for tuning performance diesels. You want to be running the turbo at its very limit the whole time, and just add and subtract fuel to add and subtract power. Power is proportional to fuel. Just got to have the air there to make sure it doesn't get too rich. Alright, so just some overview to start with. Kind of helping, it helps to understand what actually creates boost when you're tuning a diesel. And with the petrol engine, I didn't find the knowledge of how, what actually made boost to be necessarily useful for being able to tune boost control on a petrol engine. But on a diesel, I think it's worth understanding what actually makes that little turbine spin. So long story short, it's leftover energy from the combustion. So to kind of demonstrate why that's so different in a diesel, I just want to cover off what happens in a petrol, something you guys are used to. So if we take a typical Japanese 2-liter, let's call it an Evo 10 engine, and we run 1 bar of boost, we aim and make a bar of boost, and if we run that something like 0.80, 0.85, somewhere in that vicinity, and we put the spark at the right time so our combustion's occurring at the right time, we're going to have around 700 degrees Celsius of exhaust temperature. And that exhaust temperature kind of represents the energy that's left over after combustion. That's leftover heat and pressure channeled into the exhaust system, and then therefore channeled into the vanes of the turbine housing in the exhaust. So now, no matter kind of what engine it is, around a bar of boost at a typical air fuel ratio that people would race with, it's going to get you somewhere between 700 and 800 Celsius, and I hope most of you agree that's kind of a typical number. So that means that's a reasonably consistent amount of energy coming out at that one time, and not much changes. Yes, we could go really, really rich and that would be cooler, or we could go really, really lean and that would be leaner, and the exhaust temperature would go up for lean and down for coolness, and that actually would affect how you control the turbo. You'd have to change the feed forward numbers a little bit, but most of the time, generally people are aiming for a reasonably consistent tune at a bar of boost. So whether it's 0.8, like I say, 0.82, 0.80, 0.78, or lambda 0.88, it's the aim normally for that engine is to run that consistent lambda aim, and therefore it's a reasonably consistent amount of energy left over after combustion. Now with a diesel, that's completely different. So as you can probably tell by the way I led up to that, the diesel engine can have a very different air fuel ratio, a very different lambda at 1 bar of boost aim. So I can be running a bar of boost in my diesel engine, and I can be running lambda 3 or even lambda 4, or I could be running lambda 0.9. If I was running lambda 0.9 at a bar, I'm potentially going to be nearly 900, probably 850 Celsius. Actually, pretty similar to a petrol engine at that point. But if I'm running lambda 4 or 5, my temperature could be down as low as 200 Celsius. Maybe not that cold, but what I'm trying to illuminate to here is that the leftover energy and pressure is completely proportional to the lambda that you run. On a petrol, that's relatively consistent. On a diesel, that's very much not consistent. So depending on you can be cruising at a bar of boost or wide open throttle at a bar of boost on your diesel, and those different operating ranges mean that you're going to be changing the the lambda, or that energy, how rich that air to fuel ratio is, significantly, a dramatically different change potentially in a diesel compared to the petrol. So what does that actually mean for you as a tuner? What that means is that when you're running a lot of fuel, let's say close to lambda 1.1, which is going to be very close to smoking if not smoking, then you're going to have a lot of exhaust temperature and a lot of energy, and the turbo is going to want to make a lot of boost. If you are, on the other hand, running quite lean, somewhere lambda, say 2.0, a lot of OEs run around that kind of number, maybe a little richer than that, but let's say lambda 2, then that's half as much fuel as when you are running, or nearly half as much fuel as running, lambda 1.1 or lambda 1. So what that means is, if you're running lambda 2, you've only got half the energy left over because you're only putting half the energy in. So your wastegate position, or in the case of a variable nozzle turbo, your vane position is going to have to be completely different proportional to the amount of fuel that's going in. So that's factor number one. The main things that you are looking at, or the main changes in your boost control, are the aim of the boost is again going to be usually quite a large different range of aim boosts. On a petrol engine you might have a range, say from 1 to 1.5 bar, and that might be your entire range. So when you're at half throttle, coming out of a mid corner on a petrol engine, you might want your lower boost level of say 1 bar, and then at full throttle down the straight, when you're trying to get past the guy who's been in front of you for the last half hour, you might want your maximum boost that you're going to run, and that probably is only about 1.5, maybe 1.8 bar of boost. That would be, you wouldn't normally range much more than 1 bar difference from your lower boost rating to your higher boost rating. So in a diesel, is that different? Yes. In a diesel, because of variable vane turbos, we can be easily aiming for half a bar of boost, because it's not like most diesels at least don't have a spring type wastegate. So my boost aim range might range from 0.5 bar or even lower, and all the way up to 4 or even 5 bar. So that means I have a large amount of control to work on, because I'm going across a very large different pressure range, and so I've got a lot of work to do to get all those locations, all those different boost levels correct. Alright, so lots of different aims with diesel. Our engine speed normally on a petrol engine doesn't change our boost control that much, doesn't actually change our numbers on say a remote wastegate that much, but on a diesel engine with a variable nozzle turbo it changes enormously. So we'll talk about variable nozzle turbos on the next screen, but effectively as the airflow increases with engine speed, our vane position on our variable nozzle has to change. So we get a large control difference from low engine speed to high engine speed. So large number changes there. So not at all like a remote wastegate. So we get different volumes of fuel, i.e. different lambda ranges, different amounts of boost, and across a wider range, not a wider range of engine speed, but engine speed also affects a lot how we're going to control the turbo. So like all control systems, the general plan is the same. We start by tuning our feed forward table, and then we do our PID to lock it in and get it as accurate as we can. So that's an overview of what's going on our diesel turbo, and which should be sitting in the back of your mind as you go through the process. Right, next slide. Alright, so what do we see for different actual physical turbos on our diesel? So I've started with the less common one at the top. So this is a remote wastegate that you might see very typically on a petrol engine, on a modified petrol engine with a turbo that's larger than normal. And on racing diesels it is common to have a larger turbo fitted, so in some cases you will see a wastegate system like this, so not a variable nozzle turbo. And significantly easier to tune with regard to the engine speed element. In fact, both, even the fuel element. This effectively just runs a spring, and you get some control using PWM over and above what the spring is. And yes, it will be affected by fueling, but it certainly doesn't have the effect of engine speed the way a VNT turbo does. So it's out there. Some race engines are going to have it, and it's okay to use as a means of boost control. But generally, this style of turbocharger, without having variable nozzle, the variable vanes, means that you're operating under quite a small engine speed range. So as low as maybe 1500, only 1000 revs. So it really doesn't suit a broad torque curve, and without any boost, a diesel, it's very difficult to get a diesel to build power without smoking. So this style of turbo is not ideal, certainly for general use, and only limited racing use I would suggest you would have this on. So the vast majority of turbos that you're going to see on your diesel are going to be variable nozzle turbos. So VNT is the description for them, and these take a few different forms. Effectively, a variable nozzle turbo has little vanes inside that can close up the AR ratio and make it appear like it's a small turbo, or if they open right up, it can make it appear like it's a large turbo and allow a large exhaust flow. So it's like having a T2 or a T5 all in one turbo. So these vanes are all they pivot around on little shafts through here, and all linked by a ring at the back of the turbine housing, and that ring has a lever on it that has some sort of actuator to open and close these vanes to allow the turbo to build boost at low revs or to make boost at higher revs. And at those higher RPMs where we've got a larger exhaust flow, we want those vanes to be open, otherwise it becomes too restrictive. The exhaust back pressure gets too high. So there's lots of methods of operating these levers to control these vanes. Some of them run little DC servo motors with feedback, which is quite nice. Some have PWM controlled stepper motors with no feedback. Some have vacuum actuators on them, and they just run off a spring, which is almost like our wastegate up here. So yeah, there's lots of different methods, and it's up to us to configure the M1 to understand what's on your diesel engine to make it operate. So that's in the setup parameters for the turbo setup. And once you get that right, then from that point the control and the tuning is pretty much the same for all of them, almost anyway. What we're going to do is we'll go through variable nozzle turbo tuning in our live, not live, but on a more of a hands-on webinar coming up. But for now, we're just kind of going through what we've got for options out there. All right, just before we move on to our last slide for the day, just something that caught us a while ago. We had problems getting a turbo to spool. It's on our Hilux downstairs, and it was quite laggy, and what we eventually tracked down, or it actually was tracked down by one of our customers, it was actually on their one, that the exhaust gas recirculation valve was open. There had been a wiring problem, and instead of the default wiring setup driving the actuator closed via a solenoid and a little vacuum valve, the little vacuum valve was going the wrong way, and the exhaust gas recirculation valve, which moves exhaust from the exhaust manifold to the inlet manifold, was wide open. And what that meant was the boost, the turbo still overcome the hole. The hole's not a large hole, so it still made boost, but it was quite slow coming on to boost. So just to show you what happens, I actually manually drove this valve into different locations and tried to hold the engine at a consistent operating point. And this is just showing the boost pressure dropping as I'm opening the valve, because it had feedback on it. Alright, so just something to be aware of. A lot of the common racing diesels, the first thing they do is remove the exhaust gas recirculation valve and put a plate over it. It's there for emissions. Your vehicle might need it to keep in emissions, so don't necessarily do that, but at least be aware that it should be under control by the computer and only opened and closed at appropriate times. Alright, so just a final tip on again, just on the overview of how we're going to do our boost control without getting into it now. We've got in this case, the only way forward to get good control, because we've got so many different parameters or things that affect where that turbo needs to be positioned, where those vanes need to be positioned. We effectively have three things determining where the vane should be located for any given aim. So, well, not for any given aim, but we have three things that determine what numbers to use for proper boost control. I suggest you on an M1, of course, you can put these three axes in any location you like. I suppose before we talk about that, we should talk about what the axes are. So we have fuel mass. We've already established that basically more fuel, or the richer it gets, the more fuel you add to the engine, the more leftover energy we'll have, and the more the turbo will want to spool. So that's one element of what controls the location of the vanes. The other element is the engine speed itself. So as the engine speed changes, then the position of the vanes need to change. So at high engine speeds and high exhaust flows, our vanes need to open up, and then our third element that controls where these vanes are located, the numbers that you use, is our actual boost aim. So that's the three-axis table that we're dealing with. And so my suggestion to you is to put the fuel mass and the engine speed on the two common axes, and then have a table for each different boost aim. And the reason for that is that once you get the kind of general shape of this, the numbers in this feed forward table, then higher and lower boosts will just be a similar shape, but the numbers will be lower for lower boost and higher for higher boost, as you can imagine. So let me just explain what the trend of these numbers should be. Of course, all your engines are going to be different, but generally all feed forward tables will follow this same pattern for a variable nozzle turbo. And the reason I'm going through variable nozzle turbos is that's the vast majority of diesel tuning will have one of those variable nozzle or variable vane turbos. So generally, if the amount of fuel is low, and in other words, the lambda is going to be very lean at these low milligram numbers, then your vanes are going to be tight. So 100 means make more boost, i.e. close the turbo down tightly, close the vanes. So the higher the number in the table, it means you're trying to obtain more and more boost. And these are the feed forward points for the, in most cases it's a PWM signal going to our variable nozzle turbo. It gets, in the case of a DC servo, it gets converted through a translation table to go for a particular aim, but we realistically want a big number in our feed forward table meaning more boost, and a small number meaning less boost. Big number meaning close the turbo tighter, close the vanes. Smaller number meaning open the vanes up. We're either got high flow and high volumes of fuel. So for any given aim, we need a lower number to keep that boost at the same aim. So let's just look again at where we're at with this particular example feed forward table. So we have boost control feed forward main in percentage. And you can kind of think of this pretty much like driving the duty cycle on a normal remote wastegate. It's percentage of duty. Alright, so in this case we are looking at the 17, it's actually 1.2 bar boost aim table. So when our boost aim is targeting 17 pounds of boost or 1.2 bar, the control system will use this table, use these numbers as the starting point for the PID. Alright, so the aim here is 17 pound, if we can think of it, keep that in mind. So when our fueling is low at idle, low pedal positions, usually you're going to mean low fuel mass and lean lambdas, we want to run that turbo is going to run as tight as it can. So let's just choose, in this case, the engine where our captures happened at about 3200 revs. And if we go up the vertical column, I should say, so if we're on a dyno and the dyno is holding it at 3200 and we basically just put our foot on the pedal and increase the volume of fuel, then to maintain our 17 pound boost, you can see that we have to start opening the vanes up. And the more fuel we add, the more we've got to open the vanes on the turbo to maintain the same boost. So that's the trend we should see based on fuel. As fuel goes in and the engine develops more power, the lambda gets richer, then the trend for the numbers or for the vanes is to open. If we start at 2000, let's say we have a consistent 100 milligrams being delivered, so the driver might have his foot flat. Our fuel mass limit table might be limited to 100, and we're not allowing any more than 100, and we've got no limit tables pulling anything out from 100. So we're delivering 100 milligrams of fuel and we're at 1700 revs or 1500 revs. You can see if we're at 1500 revs delivering 100 milligrams of fuel to make 17 pound of boost, we are fully tight or fully closed on the turbo. But as gas flow increases with engine speed, because the faster the engine goes, the more exhaust mass flow occurs. So as we go horizontally across and our engine speed gets higher and higher and higher, to maintain that same boost we need to be opening those vanes wider and wider and wider, otherwise our exhaust back pressure will get too high. Now on most engines the trend I see is as we get, and this is for a stock turbo admittedly on this particular engine, as we get our engine speed gets higher and higher, the exhaust back pressure does actually increase despite the vanes being open. And if we want to keep maintaining our 17 pound, you'll find we have to start closing the vanes down again, which actually increases the exhaust pressure again, which means we have to keep closing our vanes, and you get to the point where you simply can't, you get to the point where you end up with massive amounts of exhaust back pressure, and you stop actually making power. Alright, so and then if we're popping over here at 4300 where the engine speed limit is, this is just a way of opening the vanes up to stop an overboost situation, because as the engine speed limit comes in, fuel gets removed and that fuel mass comes down this part of the table, and just to stop the turbo over spooling, and you get the potential for a boost over spike. Then as we approach the engine speed limit, then we can open the exhaust vanes again just to stop that boost pressure over spike. Alright, so that shape that you see there, that is pretty much a typical shape, and that shape will be the same on the 14.5 boost request table and the same on the 7.3 boost request table. The numbers will be obviously lower, but the general trend of these numbers will follow that kind of trend. So pick one aim boost, get that feed forward and the control right for that aim, and then progress down through your different aims. Now obviously in between 14 pound and 7 pound you have interpolation of the numbers, so most of the time we don't mind if the boost aim isn't perfect at cruising speeds, things like that. You might want to cruise at 7 pound, 10 pound. It doesn't actually often matter that much whether it is 7 pound or 10 pound, because the lambda is running at say 2 or lambda 3, and the driver has control of power not via the boost but via the amount of fuel he puts in. So if the driver wants more power, he simply puts his foot down and all that does is add fuel, and that's where the power comes from. The lambda might go from lambda 2.5 to lambda 2, and the boost it does affect the power a little bit, but nothing like what happens with a petrol engine. So alright, so that's it for today. That's just an overview of the considerations of boost control tuning. And when we get into it, as I say in a later webinar, then I want you to be thinking about all of those things that can affect boost. One of the biggest ones that's going to be of new, a new thing for you is fuel. It's definitely fuel. As the fuel goes in, it just makes boost. One thing I forgot actually, that isn't mentioned, is not accounted for here. If you are running very retarded timing via very long pulse widths because your injectors are starting to be too small, you've taken a standard engine and you're running say double the boost on it, your injection times will be getting long, and what that does, if you don't increase your injector timing appropriately, the fuel ends up in the exhaust, and that also affects your boost control. So if you're running inappropriate injector timing, that can change your boost control. So just again something to be aware of. So the boost control, like the fuel pressure control, like the injector calibrations, are all things that you are constantly working from one to the other, and in a circular kind of fashion. You work on a little bit of boost control, add some fuel, get the injector timing right, go back to your boost control, check your fuel pressure control, and you're constantly moving amongst all those tables to make sure that everything's staying right, and you're tuning all of them together, and you work your way kind of cyclically around to build more and more boost, more and more power, and that's kind of the crux of it. Alright, so that's it now this time, and thanks for listening, and we'll catch you for part 6 very soon.